Okay, so we obviously did talk about the first chapter where we talked about the atom and several sort of experiments that led to the understanding of the structure of the atom. Some important highlights from that, we talked about really Thomson and the CRT type instruments that he used, and we also had Milligan and his oil drop experiment. And really, these were two really big sort of experiments that help us better understand the electrons. After that, again, sort of a early model of the atom sort of came about from Thomson, and Thomson basically said that the atom was that sort of plum pudding model. And again, that was sort of the model where we had this sphere of positive charge with electrons sort of embedded inside. There's sort of the accepted model of the atom, really to the next sort of major event that came along, which was Rutherford and his gold foil experiment. And based on sort of Rutherford's gold foil experiment, they anticipated that when they shot these alpha particles, which are those radioactively positive particles, that they would see them kind of go through and there would be some deflection, because obviously, as we talked about, things with similar charges are repelled to each other and things with opposite charges are attracted to each other. So we're shooting these positive charged particles, which are moving really fast at really this sort of mesh of positive charge. So we would expect it to pop through, but there should be some deflection. What they actually saw for the most part was that when they shot the alpha particles, most of them went through really, not like I drew there, undeflected. And every so often, though, they did see sort of alpha particles bounce off at really large angles. So what that made them sort of decide was that they had to sort of revisit the idea of Thomson's model of the atom and sort of start over and go that this is not really the correct model of the atom, and that the atom was mostly empty space. It also had a very dense positive core, which was known as the nucleus, and most of the mass of the atom was the nucleus, which is also deviates from sort of the plum pudding model, where most of the mass of the atom was believed to be the electrons. Along the way, other particles obviously were discovered, like protons and neutrons, and ultimately we end up with really sort of our really modern and current version of the atom, which is obviously we have a nucleus that has protons and neutrons in it, and out from the nucleus at some point in that empty space are electrons that are basically moving around. Any questions on any of that stuff there we talked about last time? So to continue on, we're going to talk about atomic numbers, mass numbers, and isotopes for atoms. So let's talk a little bit about each of these. So first off, isotopes, which sort of the existence of isotopes really disproves part of Dalton's atomic theory. If you remember, he said that, atoms of the same element are pretty much identical, but the existence of isotopes really sort of disproved that. And isotopes are really the same element, but they do have different numbers of neutrons. So because they have different numbers of neutrons, they also will have different masses. So they obviously are not identical to each other. The thing about isotopes is they pretty much will do the same chemistry, and that's because most chemistry is involving electrons. And since electrons really don't change all that much in isotopes, all the bonds breaking and making, one isotope will pretty much behave like another isotope. One of the advantages of that is in research, for example, you could use a radioactive version of an element, and you can really follow, for example, a particular element where it goes in a procedure or a process by following the radioactivity. I used to do experiments with radioactive copper, which pretty much works the same way as normal copper in your body, but you can follow sort of the radioactivity throughout the process, and you really can know where all the copper sort of ends up in a pathway, for example. And again, it will basically behave like normal non-radioactive, if you will. versions of that element. So obviously these are two isotopes of sodium. We have 11 protons and 12 neutrons over here, and what is sometimes referred to as sodium 23. And here we have 11 protons and 13 neutrons here, and what is sometimes referred to as sodium 24 in this case. And as we can see, probably from this picture here, and probably make a pretty good estimate guess, the one that is really important in terms of determining what element we're dealing with is protons, electrons, neutrons. It is the protons, right? 11 here, 11 here. So it really is the number of protons in the nucleus, which really determines what element you are dealing with. And if as long as you don't change the protons, which normally does not happen in a normal chemical reaction, then you will have obviously the same element. So let's talk a little bit about that number, and that is actually what is known as the atomic number. So the atomic number, which is sometimes abbreviated as a Z, is the number of protons there are in the nucleus of an atom of a particular element. That means that if that is the number of protons, that is really how many positive charges you have in an element or an atom. And if it is neutral, that means that all the negative charges would have to balance that out, which means if you have a neutral atom, the number of protons and the number of electrons will be the same. So they will balance each other out. So it will also tell you the number of electrons there are in an atom, again, in a neutral atom. That is important. One important definition, though, is the actual definition of atomic number is just the number of protons. So if you're ever asked what is the definition of atomic number, it is solely the protons. But the side note to that is, as I just mentioned, if it happens to be neutral, it will also tell you the number of electrons there are. Now, the identity of an element can be determined by the atomic number, which is the number of protons. And frankly, you could find them there on the periodic table. And if you go to the periodic table there and look over, you can find the atomic number there right on top. So that is the atomic number. If you also look at the periodic table and you look at all the numbers there are up there on top, there's not one number that repeats. So what that means is, again, every single element has its own atomic number. Every single element has its own number of protons. No two elements can have the same number of protons or the same atomic number, which is basically the same thing. So that's why I said on the previous slide, when we looked at sodium, that they're both the same element, they both must have the same number of protons. Again, you would never find a calcium atom with an atomic number of 19 or a number of protons of 19, and that's because 19 is potassium. So number of protons really, really important. Nitrogen's atomic number is 7, which is the number you see above N on the periodic table. It means in a neutral nitrogen atom, it will have 7 protons and also 7 electrons to balance out the charge. And again, in a normal chemical reaction, which is what we deal with in this class, there is no touching of anything in the nucleus where the protons are housed. It is just the electrons. So those guys never change in a normal chemical reaction, which is why we balance all the equations and have the same number of elements on both sides of the arrow. Another really important number is the mass number, which is sometimes abbreviated as an A. The mass number is the number of protons and the number of neutrons that you find in the nucleus of an atom. So mass number is protons and neutrons. Now, except for hydrogen, which actually has only a proton and only an electron, hydrogen does not have a neutron. Every other element will have protons, electrons, and neutrons, except for hydrogen, obviously, again, does not have that neutron. The importance of the mass number and atomic number is this: if the mass number is protons and neutrons and the atomic number is protons, you subtract those two that will give you the number of neutrons there are. So if you take the mass number minus the atomic number, that will give you the number of neutrons there are. All those things that you're sometimes asked to calculate, which is the number of protons, number of electrons, number of neutrons, the mass number, and the atomic number, they all should be positive whole numbers. So they all should be positive whole numbers. Can we find the mass number on the periodic table? The answer is no, you cannot. So that top number, once again, is our atomic number. This number on the bottom here is not the mass number, although sometimes people want to call it the mass number. It is not the mass number. It is what is referred to as the atomic mass, and in some cases we use it for the molar mass, but it is not mass number. One easy way to remember that is, frankly, it needs to be a whole number. So if you look at pretty much all the bottom numbers on the periodic table, there's like no whole numbers for the most part. They're all pretty much some type of decimal type number. So do not be the person that writes that number from the periodic table on the exam. Otherwise, you get the X on that question. So how do you figure it out? You will have enough information in those type of problems to figure out how many neutrons there are, and you should calculate it from the information that's given to you in the problem. Either you might be given the mass number, you might be given maybe the number of neutrons if you had to calculate the mass number. So you'll be given that type of information or enough information that should allow you to calculate it. So really the only number you can find off that periodic table, the atomic number. Any questions on that? Now, in most cases, as I mentioned, isotopes have different masses, really because they do have different numbers of neutrons. Hydrogen, for example, has one proton and no neutrons, as I mentioned. Every other element will have a neutron. Deuterium, which is basically heavy hydrogen, has one proton and one neutron. Tritium, which is like the radioactive version basically of hydrogen, has one proton and two neutrons. These again are all basically isotopes of each other. One way that we very commonly write sort of isotopes is we use the symbol, as you can see there on the bottom, represented by the X. On the top left of the number, we put the mass number. On the bottom left of the number, we put the atomic number. And that's one very common way to do it. Another common way that you see it, a little less, but you still sometimes see it, for example, is like copper 64. This number here would be the mass number. I know it's not the atomic number because if I go to the periodic table, I could look at copper and see that the atomic number is 29. And obviously that would be the atomic number of protons. So if we were to write these symbols for each of these things, we would look at hydrogen. And if you weren't sure what the symbol is for hydrogen, you could go to the periodic table basically and find number 1, and you would find that it is H. You would also put the atomic number on the bottom. The mass number, which is found by taking protons and neutrons, that is 1 plus 0, which gives me 1. And that would be the symbol there for hydrogen. I'm sorry? It is not. So when we write it like this, most of the time, we use this format down here. Sometimes in writing and problems, they'll sometimes write the isotope like that. But most often when you're asked to write it with the mass number, atomic number, you should write it like that. Yeah. Other questions? If we look at deuterium, which once again, we might not know is hydrogen, we could figure it out that it is hydrogen by looking at the periodic table and seeing number 1. So that tells us again, we should put the same symbol. The atomic number is 1. Here again, our mass number would be 1 plus 1, which would give us 2 in terms of our mass number up on top. And lastly, tritium, once again, the name doesn't sound like hydrogen, but that 1 proton tells us it is hydrogen. So we will use the symbol once again. And lastly here, 1 plus 2 would give us 3 for our mass number. And those would be the symbols for hydrogen, deuterium, and tritium. Basically, we take the top number minus the bottom number when we have the symbol written like that, and that gives us the number of neutrons. So in the first one, if I took 1 minus 1, that gives me 0 for the neutrons. For the second one, if I took 2 minus 1, it gives me 1. And for the last one there, if I took 3 minus 1, gives me 2 for the number of neutrons. So if you have it written sort of in that form, top number minus bottom number will give you the number of neutrons. Any questions on that there? Okay. All right, so for each of these, take a moment and figure out how many protons, electrons, and neutrons we got going on in this situation. Okay, let's take a look and see how we're doing. So once again, we're looking for a number of protons, electrons, and neutrons that we got going on here. So here we start with cobalt. And we take a look at here. We know the bottom number is our atomic number. Top number there is our mass number. So the atomic number does tell us the number of protons. So in this case, we should have, for protons, 27. This is a neutral atom. The reason I know that is where I look right about there. There's nothing written, so there is no charge. So we could assume safely that it is neutral. And because it's neutral, the only other particle that has a charge in an atom are electrons, which are negatively charged. And that means that we do need to have an equal number of negatively charged electrons, giving us an overall charge basically of 0 in this particular case. Our number of neutrons would be found by taking the mass number minus the atomic number. So neutrons would be, in this case, 60 minus 27, like a 33 maybe we'll go with in that particular case. Any questions on that one there? Looking at the next one, which is chlorine. Once again, we see it's neutral. We don't see any charge written there. We're going to look at the bottom number there to tell us the atomic number, which is 17. So once again, this will have 17 protons. It will also have a matching number of electrons to balance out the charge. And looking at our neutrons, we got 37 minus 17 in this case. Mass number minus atomic number, going to lay us up a 20, I think, on that. Any questions on that one? And lastly, we have U, which is uranium. Also, again, neutral, nothing written there. In this case, our atomic number is 92. So we got, in this case, 92 protons. We got, again, an equal number of electrons to balance out the charge. And our neutrons, in this case, would be 238 minus 92. That's a lot, like a $1.46 maybe, like that, yeah. Any questions on any of those calculations there? Okay. Now, not always will both of those numbers be given to you. Sometimes they may not give you the atomic number, but that's okay. You can go to the periodic table and, again, easily find the atomic number if it's obviously not provided to you. They may not give you the mass number, but may give you the neutrons. So again, you could go to the periodic table, find the protons, and add it to neutrons to get yourself to the mass number. Any questions on that? All right, let's try a few more here, maybe. All right, so why don't we write this symbol with the mass number and the atomic number for each of these? Krypton, nitrogen, and iron. Let's also give the protons, electrons, and neutrons for that guy. All right, let's take a look here and see how we're doing. So obviously we go to the periodic table and find our symbol, and that should be Kr there for krypton. So we lay up a Kr. In this case, we could also go to the periodic table there and find our atomic number, which I believe should be 36, which would be the number there on the bottom. That 36 would be the atomic number, which means it also is the number of protons there are. It gives us the number of neutrons, which is 48. So once again, we do want to add our protons and neutrons together to figure out our mass number, which in this case there looks like an 84 when you do that there. Any questions on that one there? We obviously could assume it's neutral, as it wasn't mentioned anything about a charge in this particular case. Going to nitrogen, which is N. Once again, we could go to periodic table, look at N, and we see number 7 there for our atomic number, which once again gives us our 7 protons. We can use the 6 neutrons that they told us about there to get us to our mass number, which should be 13 in this case. And that will give us our 13. Lastly here, we're looking at iron, which is Fe on the periodic table. And once again, from the periodic table, we could find the atomic number, which is 26. In this case, they were nice enough to give us the mass numbers, so that would be the 56 that we need in that case. We also want to know protons, neutrons, and electrons. So in this case, our atomic number obviously would be 26. It is neutral, so we will have a matching number of electrons. And lastly here, for our neutrons, we'll take our mass number minus our atomic number. And that gives us 30 for the number of neutrons. Any questions on any of those there? Questions on how to find protons, electrons, neutrons, mass number, atomic number? Professionals, I like it. All right, so none of these had charges, but let's talk about what would happen if we did have something with charges. Things with charges are known as ions. And there's really two types of ions. There's cations, which are positively charged, and then there's anions, which are negatively charged in this case. So let's say we took maybe that last one there, which was iron 56. And let's say we laid up a +3 charge in this case. That would be a cation. And if we look at what we had going on for iron 56 with no charge, like we had on the last one, we had 26 protons, we had 26 electrons, and we had 30 neutrons in that case. So here we would look at it and we would still have the same atomic number, which means it does have still 26 protons. It would actually still have, in this example, the same number of neutrons, as we would take 56 minus 26. So our neutrons would still be the same. That means obviously here, the thing that changes is the number of electrons. How many electrons would it have? Electrons here, it would have 23 electrons, right? 23 negative things, 26 positive things. Leaves us a +3 left over. And again, that is where the charge comes from in this particular case. It is the number of electrons. And it's something that becomes positively charged if we compare it to its neutral counterpart. Has less electrons, so it actually lost electrons. And that's how cations are formed, by losing electrons. The plus tells you that the ion there lost electrons. The number tells you how many electrons it lost from the neutral elements. Yeah. Any questions on that there? What's that? Charge entities? Other questions? So let's take a look at what happens with our anions. Our negativity guys, we'll do our nitrogen, which I think we also looked at there, 13.7. Actually, we'll give a -3 charge in this case. And we'll do our nitrogen that had the no charge. Once again, the nitrogen with no charge, as we saw previously, has 7 protons. Also had 6 electrons. Oh, I'm sorry, not 6 neutrons. It had 7 electrons there, gives us no charge, and it had 6 neutrons in that case. So once again here, this would obviously have 7 protons. It will also have the difference there of 6 neutrons by taking 13 minus 7. And once again, in this case, it does have a negative charge, so it actually has more electrons. So it has 10 electrons in this case, 10 negatives and 7 positives. Leaves us a -3 left over. And again, that is where the charge comes from. So when we look at nitrogen from its kind of neutral to its guy with a charge, it actually gained electrons. Neutral nitrogen has 7. Nitrogen with a -3 charge has 10. And that is how anions are formed. They gain electrons. How they're really formed is the cation loses electrons and the anion gains electrons in this particular case. Any questions on that? Okay. So why don't we try a couple here? Let's say we had a nickel with a +4 charge. That is 28 and 60. Let's do sulfur with a -2 charge, 16 and 34. All right, protons, electrons, and neutrons in each of these things. Okay, let's take a look here. So first one there, we got nickel with the +4 charge. We will use our atomic number, which obviously if it was not given to us, we could go to the periodic table to find it. And that would mean in this case, it does have 28 protons. Has a +4 charge, which means, again, it has lost electrons and has lost 4 electrons from the neutral guy, which also would have 28 electrons. That means we take 4 away from those, we will end up with 24 electrons, giving us that +4 charge that's left over. And in terms of our neutrons, once again, we'll take our mass number minus our atomic number, and that looks maybe like a 32 or something like that we got going on there. Any questions on any of that there? Looking at S, which is sulfur, which is making a -2 charge. Once again, we could look at our atomic number there. That gives us 16 protons. The -2, the minus tells us we've gained electrons. The 2 tells us it's gained 2 electrons from the neutral. The neutral guy would have to have 16 electrons to balance that out. So gaining 2 would take him to 18 electrons, giving you that -2 leftover charge. And once again, here, finding our neutrons by taking 34 minus 16, which gives you something there, 18. Any questions on that? So you do obviously need to be able to figure out protons, electrons, and neutrons there with things with charges. Clearly, as we talked about, it is the protons that basically tell you what element you're dealing with. So you should never, ever change the protons. Otherwise, you do change what element you're dealing with. Any questions? All right. That wraps up this chapter. Energy is no longer there in the new edition. So give me a second. We'll roll to chapter 2 here. Okay, so we're off to chapter 2, which is about really electrons. So this chapter is really all about electrons, sort of where they are found in the atom. We'll also talk about electron configuration. We'll also talk about quantum numbers, where all the electron configuration kind of come from. We'll talk about the idea of waves, and we will finish up, I think, the chapter talking about the periodic table and some periodic trends, if I'm not mistaken. So why do we see colors? Really related to sort of what we're talking about and sort of starting this week with the first lab here today and the next lab on Thursday as well. We do see colors when we get something that really comes off in terms of energy or wavelength within the visible part of the spectrum. And the visible part of the spectrum, the electromagnetic spectrum, is really where we see colors, right? In the visible part. That's that Roy G. Biv. All right. And basically the context of which we're going to be talking about in this class is really about electrons. So what happens when we excite electrons from, say, a lower energy level to a higher energy level, they do have to gain energy, obviously, to get up there from the lower energy level to the higher energy level. But much of things in chemistry and kind of like life is things in sort of high energy states. It's really not what we want to happen. Things are more stable in really lower energy states. So as these electrons really get excited to these higher energy levels, what's going to ultimately happen is they're going to work their way back down to a lower, more stable energy level. The idea of the law of conservation of energy is, frankly, we can't lose that energy. It's got to go somewhere. So what happens as they are transitioning down is they typically will give off this energy in the form of a wave that has a specific wavelength, which may correspond to somewhere in that visible part of the spectrum. And thus we do see sort of colors. It's essentially what happens, right, when you watch fireworks, right? And when you see fireworks, they obviously explode the fireworks. which provides a lot of energy to those atoms, and all the electrons, they get very excited. They go off to higher energy levels. As they basically relax back down to lower energy levels, they give off that energy in the form of colors that we see. And we go, ooh, pretty green, pretty red colors and all that kind of stuff. Do all these transitions result in really colors that we see? The answer is it really doesn't. It may be outside of the visible spectrum where we wouldn't obviously see any type of color, but there could be some type of transition that is basically occurring. One of the ways that energy really does travel through space is the form of a wave. So as this wave is basically making its way through space, it will be carrying a specific wavelength. It also will be carrying a certain amount of energy associated with it as it goes through there. There's a few characteristics of waves. The wavelength, which is usually from one crest to the next, or kind of trough to trough, if you will. And that is usually symbolized by the lambda symbol. For the most part, wavelengths are given in meters and nanometers. Sometimes centimeters pops in there, but most of the time meters and nanometers are very common sort of units of wavelength. Nano is 10 to the -9, yeah. So nano is 10 to the -9. So that is a conversion you use a lot. Come Thursday in that experiment, you use it a lot, and we're gonna do some calculations, but we use it a lot. Frequency is basically how many cycles sort of a wave passes a particular point in a certain period of time. Usually the units of frequency and the symbol for frequency is really the nu, not the V, but people always call it V, but it's really nu. And it does have units of reciprocal seconds, which is 1/seconds is common units. Also a hertz is also another very common unit of frequency, and they are actually equal to each other. So 1 reciprocal second is the same thing as a hertz. So you might be given it in several different ways. Like, for example, on the radio, when we dial it into a particular station, it's like 95.5 megahertz, right? Is the frequency at which we dial our radio station in. By the way, mega also something that pops up a lot in here. Mega 10 to the 6th in terms of that prefix. The speed of the wave is a relationship of, really obviously meters per second. So if you take sort of your wavelength and times it by your frequency, that gives you wavelength in meters. Frequency in 1/seconds gives you the speed of a wave, typically in meters per second, at how fast it's sort of moving in terms of just looking at the units. Yeah. So this relationship here is an important one. You do need to know it. This is C, which is the speed of light, and personally I roll with 3 times 10 to the 8 meters per second. I don't know. I think it's just going to round it up anyways. But if you want to use it at 2.9979, you can. I think your lab manual uses like 2.998 or something like that. But 3 times 10 to the 8 meters per second is the speed of light. That is a constant. You always have that number, and that equals our wavelength times our frequency, which is basically what I just calculated a second ago. That means if we rearrange this, the wavelength is equal to the speed of light divided by the frequency, dividing this to the other side, or vice versa here. If we want the frequency, that would be the speed of light divided by the wavelength. So if you know the frequency of a wave, or you know the wavelength of a wave, you basically can figure out the other, because again, the speed of light is a constant. You do want to watch units, obviously, again, especially if you have the wavelength. The units on the speed of light are meters. So if your wavelength is obviously not in meters, you should convert it. Otherwise, you will be off by a factor of whatever your wavelength was in. So if you're in nanometers, you got to convert it to meters before you go into that equation, so everything cancels out correctly. Again, otherwise you will be pretty much off. Any questions on that there? It's super zoom. All right. So I want to try one here. Is calculate the wavelength of red light with a frequency of 4.62 times 10 to the 14 reciprocal seconds. Make sure your calculators work. I would give it a try, so you're not surprised. All right, let's take a look. So in this case, we are looking for the wavelength. We obviously have the frequencies, so that equation we just looked at would be a good one to use, perhaps. And again, that is the speed of light is equal to the frequency times the wavelength. In this case, we are looking for the wavelength. So the wavelength here would be our speed of light divided by our frequency. Once again, our speed of light is a constant, so you always have that number, even though oftentimes it is not given to you in a problem. So you always have that number there, which is 3 times 10 to the 8 meters per second. In this case, we could just go right into there, and that would give us 3 times 10 to the 8 meters per second divided by our frequency, which was 4.62 times 10 to the 14 reciprocal seconds. And again, you want to make sure you are using your exponent button. So 3 to the 8 divided by 4.62 exponent button 14, going to give you something like 6.49 times 10 to the minus 7. The units here are going to be meters, as the seconds will cancel each other out. We end up with meters at that point. Any questions up to that point? We do want, yeah. I'm sorry. Is the answer -7? So we're asking? Yeah, it is. Yeah. So 6.49 times 10 to the negative 7. And that would be, yeah, I'm sorry. Yeah, so if we're going to sort of enter this into our calculator, again, we want to make sure you use your exponent button. So you would go 3. You don't really need to put the 0.0. You could hit the exponent button. And then since this is a positive exponent, you could hit 8. Remember, you don't want to hit multiplication or anything else like that. Then you would do your divide button. And you would go 4.62 exponent button. In this case, it also is positive, so you go 14 and then hit equals. Again, if you have the E button or EXP button, that's how you'd punch it in. Remember, if you have the one with the times 10 one and the little will, as we talked about, I think the first day or second day or whatever day that was, you got to put parentheses around everything, otherwise you might not get the right answer. Other questions on that? Okay, so this is in meters, and we are looking for nanometers. So nano is 10 to the minus 9. That means in 1 nanometer, there is 10 to the minus 9 meters, not the other way around, which most people screw that up and do it the other way around. So when you see that little thing like 10 to the minus 9, 10 to the 3, that again is how much there are in the base unit, which meters would be the base unit in this case, to one of the prefix units. So we would do our 6.49 times 10 to the minus 7 meters, doing a little dimensional analysis because you're professional chemists, right? Meters, 1 nanometer. Meters will cancel, gonna yield us a 649 nanometers in this case. By the way, if you're going to punch that into your calculator, that is 1 times 10 to the minus 9. That's how you can punch it in. Or in most people's calculators that have an EE button or EXP button, you can just hit E, -9, and it will actually work for you, okay for you. We did this to nanometers because most visible part of the spectrum, colors basically, are given in nanometers as a common wavelength that they are given in. Any questions on any part of that calculation there? Yeah. You do. You would probably disregard that one because, again, like we saw on the previous slide, some people use like 2.999 and 3. I personally want to look at it. I would probably just default back to the original number in this particular case. Yeah. Other questions? And obviously, the nanometers to meters would be considered sort of an exact number, so you wouldn't have to worry about any of that that's going on there. Other questions? Yeah. All right, hopefully they agree. I hope. Yeah, looks like they do. That's good. All right, let's try another one here. we got, what is the wavelength? We'll do this one in meters of a radio station. Signal that is 100. Okay, so let's take a look. So once again, we got wavelength we're looking for. We got frequency here. So again, we're going to use up here our same equation. We're actually going to solve for the same thing in this case, which would be the wavelength is RC divided by frequency. Once again, RC is a constant, which is our 3 times 10 to the 8 meters per second. We do have our frequency, which is given to us in 100.7 megahertz. We do want to convert it from megahertz to hertz, which is really reciprocal seconds. So again, unit wise, everything will cancel out correctly. You can't go in with the megahertz or you're off by a factor of that prefix. So once again here, mega is 10 to the 6, and what that means in 1 megahertz, there would be 10 to the 6 hertz. So again, that is the correct way to use that conversion. And that means that we would take our megahertz, do a little dimensional analysis action on it. 1 megahertz is 10 to the 6 hertz. Here, the megahertz will cancel, and we will end up with 1.007 to the 8 times 10 to the 8 hertz. Again, a reminder that a hertz is the same thing as a reciprocal second. So that is the same thing as 1.007 times 10 to the 8 reciprocal seconds. So now we're in the correct units to use it in our equation with the speed of light. Any questions on that? You did, I'm sorry now, you did C over the frequency? Yeah. Yeah, that's what I did here. Yeah. That does matter, so that you want to make sure you rearrange it correctly, otherwise you'd be incorrect. So in this case, basically to solve for it, right, we would divide both sides by the frequency. That way they cancel and that gets you to the right thing. Yeah. So you definitely don't want, it does matter which way you do it, obviously. Yeah. Other questions? Okay, so now we have all that. We could go into our equation, which is the wavelength is C over the frequency, and that will give us 3 times 10 to the 8 meters per second divided by our frequency, which is now in the correct units. Once again, here the seconds will actually cancel each other out, and we will end up with 2.979, we'll call it, meters. Now, in this particular case, a couple of things. This is really a radio wave, which is on the lower end of the electromagnetic spectrum in terms of energy, but radio waves and stuff like that are typically given in meters, which is why we obviously went to meters in this case. To answer more your question about the Sig Figs, again, I would probably go here with the 4, but some people may round this to 2.98. And a lot of times you may be given direction in these type of problems because of that like speed of light sort of factor, especially like in our lab, for example, coming up on Thursday, they have you do everything to like 2 decimal places or something like that. So sometimes you'll be given some instructions on these type of problems as to how far to sort of take the answer, something like that. But without instructions, you probably could just default back to the original sort of number. Other questions or anything like that? All right. So when we talk about waves, there is a relationship between the wave, the wavelength, and actually energy. And the relationship is this: when we have a long wavelength, we have a longer frequency, and it typically has lower energy. When we talk about a short wavelength, it usually has a high frequency. So I guess low would be a better way of wording that. Low up on top. a high frequency, and it has usually high energy. So if you think about a wave where the wavelength's really sort of long, it's just kind of moving through and kind of just moving itself with not a lot of energy. If you have a wavelength that's like really high frequency, it's going to sort of pack a lot more energy. And we actually see that even with sort of colors as well. Up on top is red, green, and then we got kind of like a bluish color there on the bottom. And blue actually has a much shorter wavelength, which means, as you can see there, has a much higher frequency, occurring a lot more often, and also would carry a lot more energy than red at the very top there, where the wavelength is pretty much spread out. It's not, it has more of a low frequency and would result in low energy. So there is definitely a distinct relationship between the wavelength and sort of the energy. And the differences of sort of the wavelengths and the energy that may be given off at certain periods of time or absorbed even is what we refer to as the electromagnetic spectrum, which is this guy. And it basically gives us all the different types of waves that we see that can propagate through space and really carry energy on it. On the right-hand side here, this is the wavelength in meters. So this is a longer wavelength on this side, which means on this side should be lower in energy. On the other side, that is 10 to the minus 12, which is a very small wavelength. Short is the better word for that. Short wavelength and higher energy. So on the right-hand side there, we have things like radio waves, which, you know, FM, AM. Then to the left of that, we have microwaves, which has a little shorter of a wavelength, also then has a little higher of energy, has enough energy, right, to kind of spin water molecules really, really fast, so you get your pizza like in 2 minutes and 50 seconds or something like that. Maybe not 3 minutes, then it starts to burn, but, you know, somewhere in that range. Coming to after microwaves, we have infrared, which basically is a lot of times where we feel heat and energy, that type of process. Then we come to the visible part of the spectrum, which is here. And the visible part of the spectrum, again, is where we see colors, that red, orange, yellow, green, blue, indigo, and violet colors. And you can see in this range, in terms of the visible spectrum, these guys are usually given in nanometers. And we do see a break off of energy as well. That's like 700 nanometers, kind of like 400 nanometers on that side. And on the red side, has a much longer wavelength, which means the color red, as we saw on the previous slide, is going to be lower in energy than, say, over here at the violet purple side of the spectrum, where it has a much shorter wavelength and higher energy. So energy is increasing as you go this way in the visible part of the spectrum. And you do need to know the visible part of the spectrum and the colors and which one is highest in energy, lowest in energy. Past that is ultraviolet, which is why we put sunblock on, right? So we don't get so toasty outside, because there's a lot of energy. X-rays, also a lot more energy, shorter wavelength, which is why they throw a lead vest on you usually when you take an X-ray, and they step out of the room a lot of times as well. And gamma rays, which, as we talked about, I think the other day, is really just pure radioactivity, basically. Very, very high in energy. You need a lot of protection when you're using things that give off gamma sort of radiation if you're working with them. So this is electromagnetic spectrum, and as we're really sort of related to what we're going to talk about in this chapter, we'll be talking about is, again, as these electrons really work their way back down, they're going to give off that energy in the form of a light. And again, it may correspond to that visible part of the spectrum, as we talked about, where we would see color. But again, it could pop off in that infrared part or ultraviolet part, where we obviously wouldn't see color associated with it, but it's still giving off that energy as you go through it. Yes, sir. Which number's inside of what box? It's actually 700 nanometers. That's sort of the conversion there. Sorry. We're right at the hour where the sun comes down and stuff. So it's 700 nanometers on the right, about 400 nanometers on the left there. You need to know the electromagnetic spectrum, the different parts of the electromagnetic spectrum. You do not need to know exact numbers where things come off at in terms of wavelength, but you do need to be able to put things in order from, again, lowest wavelength or shortest wavelength to highest wavelength, lowest energy to highest energy, and obviously frequency as well. So that's sort of what you need to know for that. Any questions on any of that there? Okay. That's a pickle. So as we talk about sort of electrons and as they transfer from sort of one energy level to the next, we think of energy really as being gained or lost in really multiples of, this is really HF, I think, HV. And that is, H is what is known as Planck's constant. That is everybody's favorite number. And if it's not, it will be your favorite number come Thursday. 6.63 times 10 to the minus 34 joules times seconds. Joules is a unit of energy, and obviously seconds is a unit of time. And obviously there, that is the frequency. The idea of energy being gained or lost in these whole packets of energy is what is sometimes referred to as a quanta of energy. And the idea here is fairly a simple, straightforward one we'll talk about in this class, is essentially if I have an electron that is pretty much on that energy level and it wants to go to the next energy level, it will pick up enough energy. By the way, it would need to pick up energy to do that, right? If it had to go up in energy, it would pick up enough energy to get itself to that energy level. It will not pick up enough energy to get halfway there and go, I'm kind of tired, I'm just going to hang out here in the middle for a while. It's going to pick up enough energy to fully transition from one energy level to the next, and it may be 2 energy levels or 3 energy levels. And the same thing happens as they lose energy. When electrons sort of lose energy and they work their way back down, they will also gain enough energy to find themselves either on this energy level, that energy level. Once again, they won't find themselves basically in between energy levels. And that's sort of the idea of quantized energy. We'll see a picture, I think, in a second. You okay? One last second. One. It was 1 second. That's good. They would probably be provided for you. I imagine after some of the labs we do and the calculations you have to do, you probably will know them, but they probably will be provided for you. Yeah. The formulas will not be provided for you, but constants will be provided for you. So energy is quantized, and electromagnetic radiation is basically a stream of particles, which are sometimes referred to as photons. So a big sort of overwhelming sort of idea as we go through this chapter is the idea that particles can behave like waves, and waves have particle-like function, sort of the dual nature of light. So this relates obviously to an electron, which is a particle, so it can have some wave-like function, which we'll talk about a little bit later on in this chapter. So to figure out the energy of a photon, it is E is equal to H times the frequency. Once again, H is our Planck's constant. That's what really should be right there. I'm not sure where it disappeared to, but it should be H times the frequency there. And if you remember, to tie it into our earlier formula, which is the speed of light is equal to the wavelength times the frequency. If we solve for frequency, it would be the speed of light divided by the wavelength. And that is how we incorporate into this equation hc over the wavelength. The importance of that part of that equation is h is a constant and c is a constant, which means if you know the wavelength, you can very easily figure out the energy associated with that wave of light or photon of light by just knowing the wavelength. And obviously you could use the first part of that equation if you just know the frequency. So if you know the frequency or the wavelength, you can very easily calculate the energy associated with that photon of light or that wave that's basically going through there by either putting the frequency in or putting the wavelength in. Once again, both of these are constants that we just talked about previously, our speed of light and our Planck's constant. That is definitely a set of equations you should know. Yes. So you should know this one, and you should know this relationship as well. Yeah. You do again want to watch units when you go into here, especially with the wavelength. And again, you got to make sure it's in meters so everything cancels out correctly. And again, frequency does need to be seconds, reciprocal seconds. It can't be like megahertz or something like that that we just saw previously as well. So the idea of this dual nature like came about with the idea from Einstein equals mc squared. Energy is equal to mass times the speed of light squared. Basically, he saw that, you know, shining light on pieces of metal allows certain electrons to be basically popped off. And it had to do with, you know, the wavelength of light and even the frequency of the light. And it gives us this idea of, you know, particles could definitely have wave-like functions, and waves, again, could have sort of particle-like functions. So this brings us to what sort of happens when we kind of observe this, and we will observe it a little bit today, but most likely on Thursday as well. We sometimes will get two types of spectrums that will happen in the case of electrons basically transitioning from one energy level to the next. And the idea here is there's basically two types. One is a continuous spectrum, and that basically is where kind of all the wavelengths come off at once. So you could kind of think of it like if you were walking up like a hill, right? If you were walking up a hill, it's basically you could step anywhere you want, right? Or a road that's going up. You could stop anywhere you like along the way and stuff like that. It is not really quantized. Basically, everything's coming off at once. The sun, for example, or something illuminated by the sun will, you know, sort of give off that continuous spectrum. You got heat, you got light, you got colors. Never stare at the sun like I just did there. And I'm seeing spots probably because it's shooting right at my eyes. But metals, elements are a little bit different. Elements basically give what are referred to as line spectrums. And line spectrums are these distinct sort of lines of different colors that come off when you look at it through, say, a prism, and the light source separated out. It comes off at specific wavelengths, and you will see specific lines that occur. They are so I'll spit that out. They are so specific that every element has its own unique line spectrum. So based on the colors that you see in a particular line spectrum, based on the sort of their positions and wavelengths, you could use it to identify it. The idea of that is a more quantized approach to energy, as I was talking about earlier, that these electrons will gain and lose enough energy to really get themselves from one energy level to the next. You could sort of relate it to stairs, right? This is fine artwork here. I failed art 3 times. It's okay, but it's the trying part that's important. So when you go upstairs, right, most people will find themselves perhaps on this step or this step. Once again, when you go up a stair, you don't decide halfway through, I'm just going to lay it up there in the middle, because you will fall, right? So you typically have enough energy to go up from one step to the next, or even as you come down, you have enough energy to go from one step down to the next. And that is the quantized sort of idea of energy. Just like when people go upstairs next to you and they take like 2 stairs at a time, right? Or maybe 3 stairs, 4 stairs? No, that seems like a lot of stairs. Maybe they're really small stairs. But, you know, some people have enough energy to do like 2 steps at a time, right? And so forth. And electrons as well can gain or lose enough energy, maybe not to just has to go up 1 energy level, maybe it gains enough to go up 2 or 3 energy levels. And that's the idea of quantized energy level. I know for sure my electron will be either here, like I would be on the step, that step, that step, that step. Again, they will not find themselves in between energy levels. And that is the quantized version of energy. And that's why we get very distinct line spectrums that occur for elements, because their electrons are basically transitioning in that manner. Any questions on that there? I don't want to say that there's a fine drawing of stairs, but I will. Now, the significance of this is, again, in terms of the hydrogen atom, energies are only allowed for electrons to basically move from one energy level to the next. They're also sort of tied to the nucleus as well, right? They can't just float off and stuff like that. There is some between the negatively charged electron to the positively charged nucleus. So why is it significant that the color emitted from the hydrogen emission atoms is not white? Again, that indicates, as we've been talking about, the quantized version of energy. If it was really a continuous spectrum, we would kind of see everything sort of happening at once. And obviously, how does the emission spectrum support the idea of quantized energy levels, having those distinct waves, light lines to come off at specific wavelengths? Again, each really line that you see is related to an electron transitioning. So if you see a particular color, like in hydrogen, that may be related to the electron going from the third energy level to the second. And you see a different color, that would be related to it going from, say, the fourth energy level down to maybe the second, and so forth. Traveling multiple energy levels, right, would require more or less energy. Electrons moving multiple energy levels, it should require more energy. More energy would mean that the light coming off as the electron comes back down would be longer or shorter in wavelength. Should be a shorter wavelength, right? So we would see maybe some of those colors towards the purple side, right, of the spectrum, blue purple side. We had an electron which is transitioning maybe one energy level, right? It's not a lot of energy, which we would anticipate, and perhaps the light that would come off from that, if it comes off in the visible part of the spectrum, would be a longer wavelength, right? So maybe it'll come off towards the reddish side of that visible part of the spectrum. So understanding, how many energy levels, for example, electrons transitioning, can make a pretty good guess as to maybe what part of the visible spectrum, what colors you may see by what shows up. Any questions on that there? So that brings us to the Bohr model of the atom. And the Bohr model of the atom is a model which works really well for hydrogen and explaining sort of the lines that we see in the hydrogen spectrum, but kind of falls apart as you put more electrons in there than one, which is pretty much everything outside of hydrogen. So works real well to explain, but doesn't work so well as we move away from sort of one or more electrons. Bohr's model is sort of the planetary model where, we have the nucleus in the center and we have these orbits that go around it, where we know the electron is traveling these nice pretty circles, which, as we've talked about before and later in this chapter, we'll talk about, not really the case, but they're traveling around in nice circles where you could almost predict to put your finger there, eventually come around, right, the circle and kind of hit it. And what we see is these different orbits have different energy levels, where n is equal to 1, n is equal to 2, n is equal to 3, and so forth. N is what is referred to as the principal quantum number. It is a fancy word for basically energy level. So the principal quantum number basically describes the energy level at which you can find an electron. N equals 1 is the ground state. It is the lowest energy level. It's the one closest to the nucleus. Anything above that, like n is equal to 2 through 7, for example, those are what are referred to as excited states. And they are obviously higher in energy and further away from the nucleus. So the idea of what sort of Bohr's model described were these electrons are pretty much fixed in these orbits as they are flying around. And as they want to transition from one energy level to the next, they will pick up enough energy to do that in the form of quantized energy, like E is equal to H times the frequency. So this electron will pick up enough energy to make itself over to the third energy level. And as it decides, well, maybe I want to then go from the third energy level down to the first energy level. And that means that that electron will then lose a certain amount of energy required to do that full transition. And that sort of transition going, say, from the third energy level to the first will account for maybe the red line that we see or orange line that we see in the spectrum, or purple line, depending on what transition we're talking about. So his model is really this sort of planetary model, which was later proven maybe not so correct. And it does, though, describe really well what's happening in terms of hydrogen and the different sort of lines that we do see. Any questions on that there? So here we could see, as we were talking about sort of Bohr's model here, we see a red line that would result from the transition of going from n equals 3 to n equals 2. That's just like one energy level. So as we were talking about a second ago, that's probably not a lot of energy change that needs to happen. And that would correspond to a longer wavelength, which red is a longer wavelength. As we look at our blue transition, it's going from like the 5th energy level down to the 2nd energy level. That's like a 3 energy level jump, which is a much more in energy needed to come down, and larger energy would result in a shorter wavelength. And again, blue would have a much shorter wavelength than we would see for red. And we would see a blue line that would probably appear in our little spectrum if we were looking at it with our spectroscope, like you will do on Thursday. And obviously green in the middle there, going from 4 to 2, which is still a little bit longer of a transition, but much shorter than obviously the blue transition there. And we see a color of green that occurs. And that's sort of the same idea as what we just talked about there. So we could actually calculate the energy associated with the change of those electrons as they transition from one energy level to the next. And this is the equation. This is what is referred to as Ryberg Constant, RH. That's Ryberg's constant. Personally as well, I do a little rounded addition. 2.18 times 10 to the minus 18 is typically the number I use. But I know your lab book will use sort of a number similar to that. Oh, that sun is like perfectly in my eye. And the change in energy is equal to minus 2.18 times 10 to the minus 18 times 1 over n squared final. That is the final energy level of the electron, minus 1 over n squared of the initial energy level of the electron. This change in energy is the same relationship that we saw earlier, which would be h times the frequency, and also hc over the wavelength. So all three of those sort of equations we saw earlier can also tie into this. So if you know the transition of an electron, for example, in a hydrogen atom, and what energy levels they're going to, you can figure out the energy associated with that transition. You could also figure out the frequency associated with the wave that's going to come off and the wavelength associated with that's going to come off in that transition. When we talked about energy, I think earlier, but in case we didn't, we'll just make sure. Energy can either be exothermic or endothermic, right? And if energy is a negative number, it is exothermic, which means energy is being released. If you calculate energy and it is a positive number, that is endothermic. And that means that energy is being absorbed. So when we use this formula to calculate the change in energy, the sign that you get is really important because it will tell you whether or not the atom is sort of giving off the energy, which would be negative, or it's absorbing energy, which would be positive. So as electrons transition from lower energy to higher energy, the energy change should be a positive number for the atom. It should be absorbing the energy to allow those electrons to do so. If we're talking about electrons dropping from higher energy level to lower energy level, that energy to allow them to do that has to be emitted or released from the atom, and the change in energy would be negative and be exothermic. Any questions on that there? All right, we will lay it up there.